I'm going to continue on with the problem that was introduced in the last lecture, which is the Schrödinger equation, these linear eigenvalue problems. I want to finish that up, and then I want to get on to water waves, which is going to be an interesting lecture or two that we're going to spend a lot of effort on because it's such an intriguing topic and application of some of these ideas. Okay, so the problem that I talked about last time was this second order linear eigenvalue problem. So this is your wave function psi as a function of x. And there's a conundrum that involves this exponent p, but the idea is that if p is equal to 2, then this yields the classic quantum harmonic oscillator. The goal is to predict these eigenfunctions, psi, and then these eigenvalues e, okay, the energy levels. And you can show that for the case where p is equal to 2, the energy levels are 2n plus 1. And there's a few different ways to show this. We're briefly going to explain the classical way of doing it with WKB or WKBG expansions, but also you can do it with Hermite polynomials, and that might be the way that in a classic physics lecture you would do it in that fashion. So in the case where p is equal to 2, you can write it in terms of these special functions called Hermite polynomials. We prefer later on to convert this problem in psi to a problem in f, where in the limit that e tends to infinity, this is equivalent to epsilon tending to 0. So the transformation then would give you that epsilon n is actually 1 over 2n plus 1. So again, this is only for the case that p is equal to 2. It's much more difficult when p is not equal to 2. And you can envision the solutions of this problem on this graph here, where on the horizontal axis you have the bifurcation parameter p, and on the vertical axis you have the different energies in the problem. And so the quantum harmonic oscillator gives you these discrete energies, right, going up towards high energy, towards the high energy limit. But it was remarked that something happens if you allow the problem now to depend on this parameter p. In particular, what you find from the numerics is that the numerics predict this kind of sequence where when p is sufficiently small, and in particular when p is less than 2, the eigenvalues seem to close off in pairs in this way. Now when p is greater than 2, it doesn't happen, and you continue to have your chain of countably infinite eigenvalues. And the question is, well, how do you predict this using asymptotics in the limit that e tends to infinity, whereas epsilon tends to 0? How do you predict the fact that the eigenvalues do shut off? But even on a more basic level, how do you do your asymptotics for the case when p is equal to 2? So that's what we're going to cover. Okay. I've done some of this in a PowerPoint just so I can go a little bit more quickly. So I'm going to switch to the PowerPoint now. Okay, and so this is actually the complete bifurcation diagram that I presented to you before. The numeric, so solving this linear eigenvalue problem numerically using something like MATLAB gives you these black points. And then if you try to develop the classical analytical prediction that I'll explain to you in a second, you get the solid lines, but the solid lines you see don't capture the fact that the eigenvalues are closing off. Okay, so what does this have to do with exponential asymptotics? Let's see. Okay. So, right, this is, again, just a recap. This is the problem that we want to study in the limit that e tends to infinity. So we're just going to do a little rescaling here. Let x be this function of e, and then let epsilon be this function of e. And now we can pitch the problem in this more classical singular perturbative form where the epsilon is now multiplying the highest derivative. Now this is a problem that requires boundary conditions, right? You need to specify that the function is appropriately decaying usually in sectors of the complex plane. And to figure out what those sectors are, you can essentially do a WKB analysis for the f. So you say that f is like some exponential, and then if you study the argument of the exponential, it will tell you in what directions, in what sectors of the complex plane you have to decay in. So once you've studied that, you can impose that f then needs to decay appropriately along certain directions in the complex plane. And here I've given these directions as theta plus and theta minus. Their values are not so important to you. What you should know is that depending on what the parameter p is, then the directions will change. If in the case that p is less than 2, then you see in the lower left picture that your function f should decay going up towards theta minus in the top left, and then going to theta plus in the top right. Okay, and then these angles are specified as some function of p. But on the other hand, if p is greater than 2, then you should take f to 0 in the way that you see in this diagram here, towards the lower left, theta minus, and towards the lower right, theta plus. Okay? The classic case, the quantum harmonic oscillator case, if p is exactly equal to 0, you would want to take your function to 0 right on the axis itself. And so it's entirely a real valued problem. Okay? Okay, so this is just to review the case of the quantum harmonic oscillator, right? So f is tending to 0 as z goes to positive and minus infinity. And those are your classic eigenvalues that you can demonstrate exactly. So you can do this with your Hermite polynomials or some other way. And then you'll find that the energy levels should be just the odd multiples, 2n plus 1. Or in terms of epsilon, it should be 1 over the odd multiples. So on the graph there, on the lower graph, this is the first eigenvalue, epsilon equal to 1 over 1. And you see it's just a function that decays at minus infinity and positive infinity. And then you can look at all the other eigenvalues, so 1 over the odd multiples, and you see that they essentially consist of a function that decays to minus infinity, a function that decays to positive infinity, but then this localized region between minus and 1 where there's a series of oscillations. Okay, so the question is, so let's try to predict the asymptotics of this. In fact, I think in that graph, if you can make it out on the screen, you'll see that underlying the blue curve is this dashed black curve, which is the asymptotic approximations in the limit that epsilon tends to 0. So at 1 over 31, you see it looks very good indeed. Okay, right. So how do you get this approximation, these asymptotics? Well, the way that you would do it classically with this WKB or WKBJ analysis is you say, right, let's let f be this ansatz, a of z times e to the I phi of z over epsilon. And then you put this into the differential equation, you solve for your phi, and you solve for your a. Okay, so that gives you potential forms for the phi. They all occur. Essentially, phi prime is, if I go back to my, so up here, okay, so you see that if I substitute that into the problem, f of z totals a of z e to the I times phi of z over epsilon, then I get something like phi prime is, I think, phi prime is the square root of 1 minus z squared, or z squared. Okay, with both branches possible, plus or minus branches possible, and then the branch that you should take depends on how you want your phi to tend to in the appropriate limit. So the way that it's then written in this presentation here, okay, you can see that just for simplicity's sake, I've split the phi into each of the three regions, region 1 on the left, region 2 in the middle, region 3 on the right, and then I just take the initial point of integration in each region to be the most convenient point. So -1 for the first region, 0 for the second region, and 1 for the third region. It doesn't really matter what you take, it just makes the algebra a bit simpler. And then, in essence, your function f is then expressed as a linear combination of these exponentials and their appropriate prefactors, a of z, The prefactor you see is that 1 over 1 minus z squared to the 1/4 form. And you can see that this is why z is equal to plus or minus 1 is indicated as a turning point. It's a point where these approximations begin to break down. So at z is equal to plus or minus 1, you see a of z tends to infinity. Okay? So now you have written it in these three forms, and you have to think a little bit hard about what happens as z goes to positive infinity and minus infinity to make sure that your exponentials are decaying appropriately. But you essentially have 6 constants at this stage, right? Before we go through the constants, this is just to show you how it all matches up. So if I take the blue curve, the underlying blue curve is the exact numerical solution. So that's at epsilon equal to 1 over 11. The red curves are the approximations 1 and 3, and then the yellow curve is the approximation 2. And so now the task is for you to choose A1, A2, A3, B1, B2, B3, so that it is an appropriate match to the solution. Okay? Right, well, how do you do that? So let's just do a very basic counting argument. So there's our region 1 through 3 approximations. We have 6 unknowns to deal with, okay? You have one free normalization condition because the problem is invariant under scaling in the f in the original equation. So that's essentially equivalent to fixing one of these numbers. So you have one free constraint from your normalization. So you might fix, for instance, the value of the function at 0. You need boundedness at infinity, so that's equivalent to setting two things equal to 0, right? And then you have 4 conditions which correspond to continuity. So at plus or minus 1, you have to impose that f and its derivative is continuous. So if you're counting, that's 6 unknowns, but 7 conditions. And so that's why you think that probably the problem is overdetermined, and that gives you a constraint on epsilon. You're not free to specify all values of epsilon. Only very particular values of epsilon will give you a solution. Okay? So now you have to go through the algebra and do all of this. But at the end of the day, when you match the 2 regions, so region 1 and 2, and then 2 and 3, so you match the middle solution with the left and the rightmost solutions, it basically gives you a constraint on the A2 and B2 constants, which are from the middle solution. And you have some kind of matrix equations or some kind of linear relationship between A2 and B2 that you have to satisfy. And then for a non-trivial solution, you need that determinant to be equal to 0. And then that essentially gives you the eigenvalue condition. Okay, so when you put it all in and then you have to juggle all the phi's together and the a's together, it will give you the result that you see highlighted there. So some function of big phi is that square root of the integral of square root of 1 minus t squared. Evaluate at each of the 2 turning points, and then if you substitute the phi function into the yellow highlighted equation, you're going to emerge with the eigenvalue condition, 1 over 2n plus 1. Okay, so you see that this is nothing more complicated than just writing down separate WKB solutions, or these exponential solutions, in each of these 3 regions, matching everything together, and then emerging with some kind of selection. So sometimes they refer to this as a selection mechanism or some kind of solvability condition, which gives you these epsilon n values. Okay, and this so from this graph here, you can see that the numerical solution is given as the circles, right? And at p is equal to 0, you can see even if e is not particularly big, right? This is an approximation in the limit that e goes to infinity, but actually even at the very first one with the lowest energy value, it's pretty darn good. And it gets better and better, okay? In fact, it doesn't just get better and better. What you derived is the exact energy value. So how does it work when p is not equal to 2? And let me switch back to the board here and then just kind of explain the basic idea. So you go through the same analysis. It doesn't seem to change very much when you set p to be a general number, right? Of course, you're going to get a new function of phi, and you're going to get a new function of a. But for the most part, you think it's going to mostly be the same. So I'm going to set f of z to be a of z e to the I times phi of z over epsilon. My phi will be some plus or minus some integral from some origin of integration to z of, and in this case, instead of a t squared that occurred here, I'm going to have an it to the p. So before I had 1 minus t squared, here I have 1 plus it to the p, and then I still have a 1/2 in dt. And then I'm still going to have a is equal to some constant over, again, it's a function that is going to exhibit a singularity. This is iz to the p to the 1/4. So everything's exactly the same as the case where p is equal to 2. Okay. Well, what happens to your integration region? Well, again, you're thinking of this in the you're thinking of the function in the z plane, and in this case, when p is greater than 2, what we said is that you have to tend to infinity along some angle theta minus here, and then tend to positive infinity along theta plus, and you'll have one turning point here and one turning point here. So let me call that ZA and ZB. So this might be ZA and then ZB. Okay, and there's some path that you can take between the two turning points, just as you took that path to be along from -1 to 1 when it was originally lying along the origin. And so there doesn't seem to be anything stopping you from saying, well, I'm going to have f in region 1 here, f in region 2 here, and f in region 3 here. I'm going to apply the same procedure as before, just write down the 3 different solutions in the 3 different regions. I should have two linearly independent solutions in each region, 6 constants, kill the 2 decay ones, have the 1 normalization constant, and then do the matching required at these 2 special points where everything breaks down, and I should come out with my condition. And indeed, that's what you do, and you come out with the right condition. And that seems to give you a good approximation when p is greater than 2. The problem is, well, what happens when p is less than 2, right? So let's have a look at the complex plane again. So as I said, when p is greater than 2, you're simply going to walk from minus infinity to positive infinity in region 1, 2, and 3, and then match everything as you did so with your algebraic conditions. And if you do that, then you come out with a very similar kind of solvability condition or selection mechanism. It's going to be some function of the phi, the big phi. It's going to be some function of where these turning points are, A and B, which consists of where this the function was 0, where your infinity was produced in your asymptotic approximations. And you're going to come out with some kind of condition on epsilon n when you apply the solvability condition and you derive this problem here. So the yellow, you're going to want to solve the yellow highlighted equation for all the possible values of epsilon n, and it will tell you that epsilon n will be some function of p and a and b and etc. Okay? But then, well, now what happens if p is less than 2? This is a typo, I think. This should say procedure should fail for p less than 2. And the problem is that if you were to try this procedure, again, I'm traveling from minus infinity in the top left through the first turning point A, and then I have to go through the turning point B and then go off to positive infinity along the top right. But the problem is that if you look at your set of equations here, what you might have forgotten is that not only do I have a singularity when this quantity is equal to 0, or the prefactor of A is equal to 0, But I have a different kind of singularity at z is equal to 0. Because at z is equal to 0, if p is not equal to 2, and if p is irrational, or if p is a rational number that's not integer, then I have a branch point type singularity. So I might have p to the 3 halves or something like that. And so I have to take into account the fact that there's a special point at z is equal to 0, and that special point is associated with a branch cut. I'm not allowed to traverse through that branch cut in the usual way of thinking. And then what you find is that your path that you would typically consider, right, through from minus infinity to positive infinity, actually needs to travel through the branch cut. And it's a bit unclear what you should do in that case. So as it pertains to this classical way of doing the analysis by matching together the solutions in the three different regions, it's a bit unclear what you should be doing at this stage. Okay? So now what I want to show you is how you can resolve this problem with exponential asymptotics, with the concepts of Stokes lines and Stokes phenomena. In fact, it's actually really simple when you see it in the right way. Okay, so let's go on. So let's go back to the way that Stokes had been thinking about using WKB approximations, and to think about moving those WKB approximations into the complex plane. So here you have a picture where we're thinking of the situation where p is greater than 2, right? Where you had 10 to infinity on the lower left to the lower right. And you can write down an exponential on the lower left, right? This a e to the I 5z over epsilon, where this 5z is one of the possible branches of your solution. Okay, so this is just a solution that decays, is one of the exponentially decaying modes at minus infinity. And the way that you would think if you're Stokes is, what's stopping me from, instead of taking a path directly through the point A and B where everything blows up, let me just indent it slightly into the lower half complex plane, and I'm just going to move my approximation from one side to the other. And the problem, as you now know, is that there may be Stokes lines in the complex plane. Your exponential, the initial exponential that you considered this blue circle, is still going to be there as it gets to the right, but you may have switched on, this exponential may switch on other exponentials along the way. So the point is that there are Stokes lines in this problem that needs to be considered, right, for all values of p. So what you can do is you can go and figure out what the criterion for Stokes lines are, and you now have the tools for that. They essentially involve what you see on the top right there. So these are just conditions on the imaginary and the real parts of phi, and you have to figure what those are. But you would go to each of your critical points, A, 0, and B. You would then plot the curve that satisfies this Stokes line condition, and then you would plot it. And then what you would see is that there is a Stokes line, the blue Stokes line from A that comes down, the blue Stokes line from B that comes down, and in fact a central Stokes line from 0. Now the one from 0, you only have to consider if 0 is a special point, right? So if you are in the case where p is equal to 2, if you are in that case there, then you don't have any special point that you have to consider at z is equal to 0, because this is not a branch point. It's only the case where p is non-integer, right, and it is rational or irrational that you have to consider these special cases, because this is then an exceptional point. Okay, but you can do that, and again, this is no more difficult. Let me go back to my PowerPoint here. This is no more difficult than just writing down the phi function and then applying certain conditions on the real and imaginary parts. And these conditions are these Dingle conditions on the singular function that we've encountered in other contexts. Okay. But the idea is now that when I analytically continue my original exponential function from left to right, every time I cross one of these Stokes lines, I have to switch on an exponential. So the first one that I cross, I have to switch on this exponential, which I can derive. Then I cross another one, which switches on another exponential that I can derive. And then finally, the third one, okay? And all the exponentials, because of the way the problem works, is related to this big phi function, just evaluated at different locations, okay? And the idea is that by the time you get to the right-hand side, you need everything to be equal to 0 in order to satisfy the necessary boundary conditions. So the first exponential from A, the third one from B, and the central one from 0 if it's applicable, if the one from 0 is needed. Now, you can then look at what happens when p is greater than 2, and you find out that if p is greater than 2, in fact, the central Stokes line contribution, the one from 0, is actually smaller than the first and the third. So actually, it's subdominant, and you didn't need it in the first place to leading order in these exponentials. And so that tells you that you should only have the two conditions. And in doing so, we've essentially re-derived the way that you would have done it classically by traveling right through the turning points. Okay? But then now you can guess at what's going to happen when p is less than 2. When p is less than 2, your path in the complex plane needs to change a little bit because your function still needs to decay at the right angles. And again, but the idea is that you're still going to travel from left to right in the complex plane, and you pick up contributions along the way. And you pick up the same 3 contributions. But the main difference is that the way that the phi function works in this case is that, in fact, you still have the 3 contributions, but now the red contribution, the central contribution, actually exponentially dominates the left and the right contributions. So that's what's changed when p is greater than 2. And in this case, there are no solutions, right? In the limit that epsilon tends to 0, there's no way that you can set this single red term equal to 0. So that tells you that when p is less than 2, if epsilon is sufficiently small, there should be no solutions. And that's a sign that these eigenvalues are closing off, okay? Now, what you can do is then you can take your condition, so it hasn't really changed in the different p cases. It's still, this is still, in some sense, the leading and the next order contributions. And you can simply solve this equation that you see on the top right there for different values of p. So remember, for a different value of p, your phi function is going to give you a different number, and your a and your b values are going to be given different numbers, and your c is going to give you a different number. But you can simply solve this for different epsilons. So you set the value of p and then solve for the families, all the different values of epsilon that give you 0 for this set of equations. Okay? And what you're interested then is, how does the solutions of this equation on the top there compare with the exact numerical eigenvalues? So this was the picture that I showed to you before. The dots are the numerical eigenvalues. Okay? Now, before I show you that, I'm gonna play a video which is gonna animate these eigenvalues for you, and it's a confusing video if you're not gonna anticipate it, but I'm gonna show you a video where we're not only are we gonna plot the real part of these eigenvalues. So you remember that when p is equal to 2, everything is real, right? It's just 2n plus 1, right? But the idea is that when the eigenvalues begin to pair off, just like how quadratics, how the solution to a quadratic equation goes to imaginary when the 2 roots coalesce, you're going to have the same phenomena. So at each of these tips of these fingers, what you're expecting is that basically, if I look at the imaginary part of the eigenvalues, I should notice that the imaginary part of the eigenvalues is going to start to increase from 0. That's what you're going to see. Okay? So here's the picture, the numerical eigenvalues in the p versus real part of E plane, the energy values. And then now here you can see that actually, if you look at the diagram but allow for an extra dimension being the imaginary part of E, you can see the imaginary eigenvalues start to emerge when the real eigenvalues pair off. Okay? Also in this picture, you see the red curve. The red curve is our analytical prediction, just from solving this relatively simple set of 3 terms added together. And you can see it's a beautiful match, right? In fact, over a much larger range of eigenvalues than you might expect. Remember, this is theory for e tending to infinity, and yet you can see it looks really good even for e moderately small. Okay. All right. So that's basically it. This is the end of this chapter on linear eigenvalues. This is a really nice application of exponential asymptotics because it's a classical problem that you might have done in a physics course. You might have done it in a very particular way, just by taking approximations in 3 different regions. And yet you see that we can ask a very simple question, which is, what if we just move in the complex plane rather than right along the axis? And we can see that if you understand these concepts of Stokes phenomena and exponential switching on and off and being able to plot these Stokes lines, you can develop actually a really elegant solution to developing the eigenvalues. This idea, by the way, of eigenvalues a countably infinite number of eigenvalues, and then possibly a parameter which changes so that countably infinite set will also change, that comes up again in many other eigenvalue problems in much more difficult settings beyond just the linear case that you saw here. The example that we saw in the previous lecture was about the anisotropic crystal growth problem, right? So this was this nonlinear PDE, this nonlinear ODE model of a snowflake tip. We saw that if you had isotropic growth, so that was the classic version of the problem, there were no solutions. But then if you introduce this extra parameter, this extra anisotropy parameter, this alpha, you can get solutions because you could tune the Stokes line switching so that they would turn off at infinity. This example of the eigenvalue problem is one where you have the possibility for localized waves. So remember, the idea is that you travel from left to right, you switch on an exponential, and then you have to switch it off by the time you get to the positive infinity. But it has this unusual twist that there's a point here at the origin that screws everything up, and there is an extra contribution. So actually, if I were to plot the exponentials in this problem, I would start off with 1, I switch on 1, I switch on a small one here that's never switched off to infinity, but actually it's dominated by the exponential that is from this turning point. But now if I move this picture into the upper half plane for p less than 2, then actually this contribution from the middle grows to be larger than the other two, right? So you see, once you understand the tools, this kind of reasoning is actually within reach, and it's really quite cool. All right, so I'm going to switch now quite quickly to look at a different application of exponential asymptotics. I should say, by the way, that there's an entire community of physicists, of theoretical physicists and quantum physicists who use concepts like Stokes lines all the time. This is not new. It's been known for many, many years, for 100 years, in some sense since the start of the 20th century, start of the 1900s. People were already using these concepts of Stokes lines. But this was primarily for the case of linear problems, for problems like the Schrödinger equation, right? The kind of problems that we're now going to be moving into are really nonlinear ODEs, nonlinear PDEs. We won't get to the case of PDEs, but actually the principles are often shared between linear and nonlinear problems. They're a little bit harder for the nonlinear problems, but these concepts of Stokes lines and so forth are still there, okay? All right, so let me now show you the next application that we're interested in. We're going to move to the area of water waves, okay? And water waves, again, like it goes all the way back to Stokes and before Stokes as well, and Euler, and this is a rich area for applications of exponential asymptotics. It's rich because basically the kind of predictions that you want to make, the things which are exponentially small, are in many cases physically observable. So that's actually quite cool that you're trying to predict some asymptotics for something that is often crucial because it's observable. The kind of problems that we're interested in here, I've just taken a random selection of images, are essentially low speed or low Froude waterways, and there is a really significant history to these kinds of problems, right? So what you're imagining is basically a flow over some kind of obstruction. Now, the first kind of reference where you can find some hints that there's some real weirdness going on, which turns out to be exponential asymptotics, I think would generally is attributed to Francis Ogilvy in 1969, and he wrote this kind of paper describing some of the oddities that him and his research assistant had noticed in studying low-speed waves. So what did he write here? In attempting to solve a problem involving the motion of a body near a fluid-air interface, one generally linearizes the boundary conditions at the free surface. This is a matter of sheer necessity, for otherwise there's little hope of solving anything. Okay, and then he goes on, he says, well, generally if the first linear approximation is a poor one because the perturbations are too large, there cannot be very much hope of improving it with higher order terms. Okay. A remarkable exception to this rule appears to have been found by Neil Salveson, who was, I think, a postdoc of his or a research assistant of his. He has shown that under certain conditions, the second order solution dominates the linear solution, but also that the higher order solutions are comparatively unimportant. Okay, so that's a bit weird. So he's saying that if you try to develop an asymptotic approximation, usually you want your first approximation to be quite good. If it isn't, then adding extra higher order terms is usually not going to change the situation, but there seems to be some so-called remarkable exception to this rule. And then he says, it appears paradoxical that it should be necessary to include higher order approximations at very low speeds, for the total disturbance becomes smaller and smaller as the speed is reduced more and more towards zero. One should expect that the assumptions required for linearizing ought to become steadily more nearly valid as the free surface deflection decreases. Instead, the problem appears to become more nonlinear. Okay, so very strange idea. I don't think it's actually explained very well at this stage what the issue was, and I might explain it in a slightly different way to what you see here of what the conundrum is. Let me go on. So let me try to tell you, in a very basic way, what is this low speed paradox, or what is this low Froude paradox? And I first have to tell you what the Froude number is. Basically, our next, over the next little while, we want to tell you what, we're going to assume that you don't really know very much fluid mechanics. We're going to have to tell you what the equations of fluid mechanics are. I'm going to have to then reduce it into a form where we can do some asymptotic approximations, and then we get to use our exponential asymptotics. So there's a little bit of setup that needs to happen. Okay, so let me just kind of tell you the basic problem. So I have some kind of ship. Should I draw a ship here? All right, here's my ship. Okay. And it might be flowing through the water, but I might assume that there's an incoming flow of speed u in this ship problem. Okay, I should really always draw the flow from left to right. I've violated one of the principles of fluid mechanics, but that's how I've done it. Okay, so what are you interested in solving? So I've got some water surface here. Okay, and I would typically have some kind of wave pattern downstream. And essentially, if I assume there's no viscosity in the problem and I just have regular what's called potential flow, so this is the basic equations that you would imagine to try to apply to water, then the main unknowns are, okay, let's make a list of the unknowns. So these are the unknowns or the variables. So the main things that you want to know is, for example, the velocity u as a function of x, y, and z. But because of the problem is what's known as a potential flow problem, because you've made certain assumptions on your water, then it turns out that you can always write this velocity as a gradient of the potential, right? This phi. Okay, and the other unknown that you need to, so you need to figure out what phi is, the potential. It turns out to be simpler to work with phi than it is to work with u. And the other unknown that you want to know is a surface here. So if I set some value, some mean value for the surface, I might write my surface as a function eta of x and y. So given values of x and y, I need to figure out what eta is. And so this is known as a free boundary problem because you're trying to solve some kind of set of equations within a bulk fluid, but you don't know what the upper boundary is, and that's what makes it difficult. Right. In addition to this, you know, or you've been deriving from your fluid mechanics that actually this potential function phi satisfies Laplace's equation. So within the fluid, it satisfies Laplace's equation. Let me call this in omega, if omega is my fluid domain. And then on the boundary of the fluid, okay, I need certain extra equations that express things like the balance of pressures and the balance of forces. Okay, so the equations I need are d phi dn equal to 0 on all surfaces. So this is expressing the fact that the fluid cannot enter through the body at the solid body of your domain, and it also, any fluid particles on the surface have to remain on the surface. And then you also have what's known as Bernoulli's equation. So it's an equation that expresses a balance of inertial and gravitational forces. You have gravity waves in this problem, and it looks something like this. The details are not too important for you, as long as you know that you have some kind of equation that you need to satisfy. Okay, so this is an equation that you would have to satisfy on the free surface, on z as a function of x and y. Z is equal to eta of x and y. And then it involves a parameter here, and this parameter here is the one that's going to be crucial for us. This is what's known as the Froude number, or the square of the Froude number, Froude squared, which is u squared over gl. Okay, and here L is some length scale in the problem that you can specify later. But for example, I might take L to be the typical depth of submergence, or I might take L to be the typical size of my ship. Okay, so this is a hard problem, right? The first equation is somewhat easy because it's a linear PDE. The second equation is kind of a normal flux condition, a zero flux condition on the boundaries. The third equation is the thing that screws everything up, because basically this is a nonlinear equation. It's not only nonlinear, it's got this phi x plus phi y squared type term, but it's also imposed on a surface that you don't know. Okay, so basically this is what Ogilvy had mentioned, which is that to make any kind of progress in these kinds of problems, you usually have to make some kind of approximation, because nothing you can do with this guy, right? So what kind of approximations might you make on this problem? Well, prior to the 1960s, the classic approximation to make was what would be called thin-bodied or thin ship approximations. So what you assume is that instead of your ship having some kind of finite extent or finite depth, you assume that you're trying to study the case where the ship is really thin and is moving through the water. So, think of your ship as being approximated by a series of point sources, like a knife edge traveling through water. Okay? And so that might hopefully simplify the some of these conditions to impose. In particular, if your ship is infinitely thin, you might think that to a first approximation, the water, you can think of the water as just passing right through the ship, right? And so it turns out that actually, if the flow is coming in at speed u here, the first approximation might be that I don't even have the ship at all. I just have uniform flow right through. And so that allows you to hopefully try to simplify and linearize some of these equations. Okay? You might also consider the case that, and Lord Kelvin did in the 1800s, where the ship is approximated as a single point source. So you might say, well, suppose my ship is so small, right, viewed from some length scale, viewed from high above, my ship is just going to be approximated by a single point source moving through the water, or a single point force where the water is moving through at speed u here. And in that case, it turns out that you can then Fourier transform this problem and write down a set of integrals which describe the wave motion. And you can look that up in a classic book on method of stationary phase. So this is one of the methods for approximating integrals. There's a way to develop the wave pattern downstream and show that actually it occurs in this kind of famous V-shaped pattern. This is the Kelvin wave pattern. But what we're interested in, what Ogilvy was interested in, is can you do these kind of approximations on blunt-bodied ships, on ships where you're not going to make some kind of geometrical assumption on the body. You're not going to assume that it's going to be infinitely thin or infinitely small in one or many of its dimensions. But you still have to take some kind of approximation, so it's sensible for you to take the limit that epsilon tends to 0. So this is why we say it's low-speed flow, or low-Froude flow, that you're taking the limit that the velocity u is tending to 0, okay? And the other way to thinking of this asymptotic limit is that at leading order, you think of gravity being infinitely strong, and so essentially the free surface should be flat to leading order, okay? Well, what would it look like in 2D? Let's just talk about 2D because even that is a difficult problem. So let's consider a problem where you have some kind of geometry, okay? Right, here's your flow. It's traveling from left to right at some speed u. Maybe L is the length scale of this step or whatever or any kind of obstruction. And you're interested in the limit that epsilon tends to 0. Well, you look at this equation, right? If epsilon is equal to 0, it just tells you eta is constant, and therefore the free surface should be constant to leading order. So this is what I was saying, that if gravity is infinitely strong, you can think of basically it flattening the whole free surface out to leading order. So instead of this being your wave surface, your leading order approximation would just be eta equal to 0, if you like, if I just set the height of the 0 flow here. Okay, so this is x here, and then this is y here, and then the leading order approximation, if I think of an asymptotic approximation for eta and all the other problems, I can look at all the other problems and all the other variables in the problem. I would have an asymptotic expansion in eta, and I would have the same thing for phi and so forth and so on. Okay, and as we said, eta naught of x, if I'm thinking of steady flow, there's an interesting problem of what happens if it's unsteady. Just from looking at this thing here, eta naught of x is equal to 0. Now, you can crank the handle, and what you'll realize is that to get any higher order approximation, to get eta 1, eta 2, and so forth, because this solution here, eta naught of x, has no waves in it, it's wave free, then all the eta 1s and eta 2s, those can never produce waves as well, just because of the way the differential equation works. You're never gonna produce waves in the higher order approximation if it was not there in the lower order approximation. And so if you go with this logic, it would tell you that essentially there are no waves to every single order. And in fact, that is the case. This eta, the eta that you see in reality, is actually exponentially small. It scales with the Froude number, minus k over epsilon. And you could perform an experiment to measure this or solve it numerically and measure that. Right? And so now the question is, so this is kind of what Ogilvy had mentioned. I mean, I think even now, 50 years afterwards, if you read some of these original works in 1969, it was quite unclear what they were trying to articulate about the asymptotic expansion in the low-Froude limit. But by the mid-70s and certainly by the 80s, they understood that actually the waves that they're looking for are exponentially small. The waves they're looking for is exponentially small. And the asymptotic approximation was divergent. But at the time, they didn't really have the language for exponential asymptotics, and they couldn't really explain the consequence of this divergence. They don't see it in the same way that we do, which is that if your asymptotic approximation is divergent, there is a link to that and generated exponentials. Okay. Now, in what time remains, I want to tell you how do we write this problem here, the problem in phi. We need to, even this in 2D is a really annoying problem to work with because you're essentially having to deal with the Laplace's equation. So you're having to deal with the Laplace equation, you're having to deal with the free surface condition, and essentially for a lot of these potential flow problems, through the magic of complex variables, there's a way of reducing the problem from a PDE that you have to solve within the domain entirely to an ODE and an integral equation along the free surface. So this is similar to how you would use contour integration or Cauchy's formula to relate the value of a function within a domain to its value on its boundary. Okay, so the way of using complex variables in all this. Okay, so then how do we do that? How do we change this problem to a complex variable one and then write down these potential flow problems or Laplace equation problems as a boundary integral? Okay, and for that is mainly an exercise in me kind of telling you what the notation is going to be, and I'm not going to give you the details of how you get to the final set of equations. By the next lecture, we're just going to start with the final set of equations, and we're going to work with the analysis of those equations. This lecture is just telling you what the notation is. Okay, so let's consider a problem as we've illustrated of 2D. Okay, it's harder in 3D. But in 2D, I've got the z plane. So for example, I have x and y. Remember, I'm going to just assume that I have steady flow. So I have some kind of obstruction here. I can also consider the problem where the obstruction pierces the surface, and we're going to do that later. But yeah, so this is the problem that you're working with. And in general, what you're interested in is phi as a function of x and y, the value of the potential everywhere within the fluid and on the surface itself. Okay? And essentially, you're trying to solve Laplace equation for del square phi is equal to 0. Okay? Now, in the 1800s, Stokes realized that there's a trick to thinking about this kind of problem. And the trick is to not think of phi as a function of x and y, but to think of x and y as a function of phi. Why would you do that? Well, if I think of I want to think of the potential plane as the independent variable rather than the dependent variable. And because I have Laplace equation here of del square phi is equal to 0, then I know that I have a harmonic conjugate. So every, your function phi has a pair, this harmonic conjugate, which is called the stream function. And the stream function is equal to a constant, and you're going to assume that it's equal to 0 on this free surface, and the stream function is also equal to another constant, which you can take to be less than 0 on the lower boundary. Okay, so this is the complex variable nicety that you have, that if you're trying to solve a Laplace equation, you can introduce this, what's called this complex potential. And then there are two unknowns in this problem. There's a phi and a psi, your potential and your stream function. And so you can plot the domain as a function of phi and psi, and it basically lies within a strip. So if I call this A, B, C, D, this is now A, B, C, D. The bottom boundary has been straightened out because it lies along psi is equal to constant. And the top boundary has also been straightened out, and it lies along the real axis, the real phi axis. Okay? And remember that in the original context of the problem, you're trying to predict, for example, y as a function of x, right? Along the free surface, y is eta as a function of x. For every x value, you have a height to think about. But this is a simpler way of thinking, where you can think of y as a function of phi. So let me write that a little bit more generally. I can think of x as a function of phi and psi, and y as a function of phi and psi. So that the free surface has basically been mapped to x of phi 0 and y of phi 0. This has the nicety that basically you're then trying to you're essentially trying to solve sets of equations for x and y as a function of phi and psi, but then you know the domain of phi and psi. It's just a nice strip now. And that's why this kind of inverse formulation turns out to be simpler than dealing with this formulation. It's a bit weird to think about if you've not been exposed to this idea of inverting the variables, but that's the way it is. Okay, and so now the next step, so once you understand that you want to try to write down your set of equations in this inverse formulation way, where phi is now an independent variable, it turns out that for our version of the problem, it's convenient for us to remap this domain into the upper half plane. So I want to perform a coordinate transformation to send me from this W plane. Remember, W is phi plus I psi. And I want to send it to the zeta plane. And in the zeta plane, in essence, you're gonna take A at this point here, BC. If I call this DE, then E and D. And you basically just map the points here to the upper half plane here. So this is now, actually I wanted to map it in a slightly different way. I want the positive axis to be the free surface. I'm going to shade it for you. So I'm going to map it so that I have A, B, C, and then D, which is downstream infinity, is going to be D and E here. So that the solid boundary here, which corresponds to the bottom topography, has been mapped to the left half axis, and then the free surface, the thing that you're largely concerned about trying to get, is now along the positive real axis. Okay? And I can do this with a coordinate transformation that just simply looks like that. So if I just send the points W to the point zeta in this way, I'll do so. I have that. And then now this upper half plane is the influid region. There's no real reason to do this other than it basically makes your formulation a lot simpler. Okay? Instead of having to integrate, basically the idea is that you're going to have a tool that allows you to convert the PDE problem into an integral equation along all the boundaries of the problem. And so it's a lot easier to go from a boundary from minus infinity to positive infinity here than to go from one in which you have to kind of go from minus infinity to positive infinity, then another one from positive infinity to minus infinity. So it just makes the integrals a bit simpler for you.